Kepler came up with 3 laws that described really, really well how the Earth and other planets revolve around the sun. But none of those 3 laws addressed the deeper question of why the Earth and other planets revolve around the sun. Enter Newton again. Newton's first law, Newton's second law, Newton's third law, and Newton's law of universal gravitation. Newton, as the story goes, is sitting under a tree one day, and an apple falls on his head. And he has this epiphany. He thinks the apple fell towards his head and hit his head because the apple has mass and the Earth has mass. At that moment, or at least as the story goes, at that moment, he discovered gravity. Any 2 objects with mass exert a gravitational force of attraction on each other. Not just the apple and the Earth, but the Earth and the moon, the Earth and the sun, you and the person sitting beside you, albeit a very, very small gravitational force of attraction between you two. Any 2 objects with mass exert a gravitational force of attraction on each other. That value, the size of that force, is dependent upon how heavy the 2 objects are, and that's why you and the person sitting next to you don't feel that force of attraction. It's there, but it's a ridiculously small force of attraction, so small you're never going to notice it. It's dependent upon those masses, but it's also dependent upon the distance that separates the objects. So if you're further away from the other person, then the force of gravity is going to be smaller on you as well. Small because of your mass, maybe small because of your proximity. We drop a rock towards the Earth, it falls at 9.81 meters per second squared. But if we raise that rock up, not to the top of a building, but we raise that rock up to, 1,000 kilometers up above the surface of the Earth, then that rock's not going to accelerate at 9.81 anymore. It's going to be more like 7 or 8 meters per second squared. Even though the mass hasn't changed, the separation distance has. Bigger the mass, bigger the force of gravity. Bigger the distance that separates them, smaller force of gravity. If that force of gravity is dependent upon the masses, then that force of gravity is going to be equal to something times the masses, the product of the masses, m1 times m2. As mass 1 goes up, the force of gravity goes up in a linear way, right? Mass 1 doubles and force is going to double. Mass 2 goes up, same effect. That's why the force of gravity right between you and the Earth is so much greater than the force of gravity between you and the person next to you, because m2 is so much bigger. The mass of the Earth is so much bigger than the mass of the person next to you. It's related to the product of the masses, but it's also related inversely to the distance. It's actually related to the inverse of the distance squared. We're going to call the distance r, not d, but r. If it was me, if it was up to me, I'd call it little d, the distance that separates the center of the 2 objects. Okay, but the Physics 30 data sheet calls it r, so that's what we're going to call it. R is not necessarily a radius. In the case of the Earth revolving around the sun, the distance between the Earth and the sun is a radius. But in the case of you and the person next to you, you want to find the force of gravity between the 2 of you guys, well then that r isn't a radius because nobody's going in a circle. It's just a distance measured in meters. But that force of gravity isn't equal to the mass times the mass divided by r squared. It's equal to a constant. That's just a number times those. It's almost equal to that. It's certainly linearly related to this relationship, but to make it equal, we have to stick a number in there, a constant in there. We call it Newton's gravitational constant, and its value anywhere in the universe is 6.67 times 10 to the negative 11 Newton meters squared per kilograms squared. The magnitude of the force of gravity, notice the absolute value signs, the magnitude of the force of gravity between any 2 objects with mass is g m1 m2 over r squared. Now what about direction? Force is a vector. We need direction, right? We don't need to get it from the equation. We know the direction already. Which way is the force of gravity acting on this board marker as I drop it towards the Earth? Towards the Earth, right? The force of gravity always acts toward whatever's causing it. We don't need an equation to tell us that. Right? What about this? We've seen that equation quite a bit, right, over the last couple of months. F is equal to mg, F is equal to m times 9.81. Is that no longer valid? And if it is, why are we using a more complicated equation if it is valid? If it's not valid, why did I even teach it to you? If it is valid, why are we doing something now that is more complicated than we have to? Okay. So you're talking about the force between yours. Let me try to understand what you're saying there. You're talking about the force between any two objects of mass, like you and somebody else, or the Earth and the Sun, or whatever, right? Between any two objects of mass, and this one is specific to the force of gravity acting on the Earth. Is that what you're saying? Okay, so between this mass, which would be you, or the board marker, or whatever, and the Earth. Okay, fair enough. But even then, sometimes we'll still use this equation. Even when we're talking about you and the Earth, we might still use this equation. This is a valid equation. It is a valid equation, always. Whether you're talking about the force of gravity between you and the Earth, or whether you're talking about the force of gravity between you and the person next to you. But there's a problem with it. It's valid, but there's a problem with it. The problem is that we don't always know what little g is. When we're on the surface of the Earth, little g is about 9.81, right? When we're up in the sky, little g is a little bit smaller than 9.81. Little g caused by you is a lot smaller than 9.81. There is a little g caused by you, but it's a lot less than 9.81. We don't know what it is, right? This is a valid equation if we know what little g is. But if we don't know what little g is, if it doesn't happen to be 9.81 because we're not on the surface of the Earth, then we've got to use this equation. So you're still allowed to use this if g is 9.81, but if it's not 9.81, then you got to use this equation. All right? All right, let's take a look at an example here. 4.1 on page 206. Kind of a tricky one to start off with, actually, but we'll manage. We're smart, right? Mount Logan in the Yukon is 5,959 meters above sea level, which is about 4,500 meters above where we are right now. We're a kilometer or so above sea level in Calgary, a little bit over a kilometer above sea level. So if you were if Mount Logan was in Calgary, we'd have to climb about 4.5 kilometers in height. That doesn't sound too bad, does it? 4.5 kilometers horizontal isn't so bad. 4.5 kilometers vertical, that's harder. Anyways, the Earth's mass is 5.97 times 10 to the 24, and its radius at the equator is 6.38 times 10 to the 6. What's the difference in the magnitude of the weight of a person at the top of the mountain as compared to its base? First of all, what you got to recognize is that weight is the force of gravity. So if we want to find the difference in weight at the top of the mountain versus the bottom of the mountain, then we've got to find the force of gravity at the top and the bottom. At the top, the force of gravity acting on that person is gm1 m2 over r squared. It's 6.67 times 10 to the minus 11. It's that constant that I told you about a minute ago, times m1, which we'll call the mass of the Earth, times m2, which is going to be the 55 kilogram person. By the way, could I swap the order of those? Sure I could. William, what's 2 times 3? Good. Taylor, what's 3 times 2? 6. Same thing, right? So whether I go A times B or B times A, it doesn't really matter, right? 5.97 times 55, 55 times 5.97, doesn't matter. At the top of the mountain, the distance from the center of the Earth is 5.97 times 10 to the 24 plus 6, no, sorry, no, it's not. That's not R. It's 6.38 times 10 to the 6 meters. That's the radius of the Earth, right? That's the distance from the center of the Earth to the surface. Distance from the center to the top of Mount Logan is 6.38 times 10 to the 6 plus 59 meters. Remember, you always want the distance from the center to where you are, from center to center. This is how far I am from the center of the Earth. 6.38 times 10 to the 6 plus 59. Okay, let's, because it's a little bit ugly, let's calculate this now. All right, so what do we got here? You know what, let's get the bottom number first. 6.38 times 10 to the 6 plus 59 equals. All right, let's square that bottom number. All right, let's do the top number now. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 55. Let's divide that by the bottom, which gives me 537.045. That's the force of gravity acting on me at the top of Mount Logan. That's my weight at the top of Mount Logan. Right, Devin? Now we got to get the weight at the bottom. Now, by rights, gravity is 9.81 at the bottom, right? So we technically could use F is equal to m times g. But since we're just learning this, I'm going to use this equation again. We'll get essentially the same value. Force of gravity at the bottom is g m1 m2 over r squared. Do you think it's going to be bigger or smaller? Bigger or smaller? I think it's going to be bigger as well. Why? Why though? Why do you think it's going to be bigger? Do you think you know why it's going to be bigger? Why the force of gravity at the bottom of the mountain is going to be bigger? Take a look at this number here. R is 6.38 times 10 to the 6 when you're on the surface of the Earth, right? It's just the distance from where you are to the center of the Earth. That's smaller than R when you're at the top of Mount Logan, right? If the bottom number is smaller, then F is going to be bigger. So how much bigger? I'm not sure, but I know it's going to be bigger. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 55. Let's solve for that one. Let's do the bottom number first again. 6.38 times 10 to the 6. Whoops. Let's try that again. 6.38 times 10 to the 6. Let's square that. There's the number on the bottom. Now let's do the number on the top. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 55. Divided by the number I got on the bottom. 538.049. Is it going to be bigger? Yeah. Not much though, right? How much bigger is it? Looks like about 1 Newton, right? 1.0 newtons. What's the difference in the magnitude of the weight? 538 minus 537, the difference in the magnitude of the weight would be, I think, 1.004 newtons, which rounds to 1.00 newtons. You gonna notice that difference? No, probably not. What are you gonna notice more? Probably the weight that you lost due to climbing the mountain, right? Like that's a pretty big exercise routine, is climbing a mountain like that. So you're gonna lose more than a Newton simply burning fat climbing that mountain. Got it? All right, I would like you to have a look at questions 1 and 2 on page 207, please, at your desks. Those questions are okay. I want to take a look at one more question. This is where we'll end it for today. This is 4.3 on page 209. Talks about an eclipse. During a lunar eclipse, the Earth, the Sun, and the Moon are aligned on the same plane as shown in figure 4.19. So we see down here, look, here's the Earth, here's the Sun. It's a lunar eclipse. But we don't end up seeing the Moon because the Earth is between the Sun and the Moon, and you get no light reflecting off of the Moon, right? So you don't see the Moon. Now, if you had a solar eclipse, what would happen? Well, the Moon is, what happens in a solar eclipse? The Moon gets in between the Earth and the Sun, so you end up being in the shadow of the Moon, basically, so the Sun disappears. They have to be aligned perfectly in order to get a complete eclipse, but okay, sometimes you get a partial eclipse because it's not aligned quite perfectly. Anyways, we want to find the force of gravity on the Earth, caused by the Moon and caused by the Sun. Well, there's two forces here, really, right? There's the force of the Moon on the Earth, but there's the force of the Sun on the Earth. Okay, let's look at the Sun first. It's bigger. The Sun pulls the Earth this way. I'll call it FSE, the force of the Sun on the Earth. Now, we know that the Sun is pulled this way, right? The Earth pulls the Sun to the left with the same force, an equal and opposite force. But we don't care about that because we're not trying to find the force on the Sun. We're trying to find the force on the Earth. So even though there is a force on the Sun, let's focus on just the forces that are acting on the Earth. The force of the Sun on the Earth is to the right. Okay, the Earth is pulled towards the Sun. Now, the Earth is also pulled towards the Moon. The force of the Moon on the Earth, FME. The Moon is pulled towards the Earth is pulled towards the Moon. We don't really care what happens to the Moon here because we're trying to find the net force on the Earth. Now, the Earth isn't going to move as much towards the Moon as the Moon moves toward the Earth because the Earth is heavier. But in the end, it's still the same force. It's kind of like, that smart car, semi-truck thing, right? Push the smart car with a certain force, push the semi-truck with the same force, the smart car moves more. Same force, but the lighter thing moves more. All right, what do you think we're going to do with this? You guys know this, right? You guys know this. What do you think we're going to do with this? We see two forces drawn here, one to the left, one to the right. What are we going to do with it? Devin, what do you think we're going to do with that? I think you know. Good. F net is equal to the sum of the forces. FME, the force of the Moon on the Earth, plus the force of FSE, the force of the Sun on the Earth. Now, we're not looking for acceleration, so we'll just leave it as F net. But we got to find these values, right? The force of the Moon on the Earth, well, that's equal to gm1m2 over r squared. That's equal to 6.67 times 10 to the minus 11 times the mass of the Moon, which is 7.35 times 10 to the 22, times the mass of the Earth, which is 5.97 times 10 to the 24. Divided by the distance from the Moon to the Earth, which is this distance right here, the separation distance from the Earth, 3.84 times 10 to the 8. And we square that. Let's say 6.67 times 10 to the negative 11 times 7.35. It's kind of ugly with the calculator, right? So many exponents. Times 10 to the 22 times 5.97 times 10 to the 24. Let's divide that by, use some brackets here, 3.84 times 10 to the 8, and then square it. We get a force of 1.9848 times 10 to the 20. That is a big force. But listen, if the Moon is going to stay in orbit around the Earth, then there's got to be a big force because the Moon is heavy. You can't keep the Moon in orbit around the Earth, something with that much inertia, by applying a force of 100 newtons. Let's find the force of the Sun on the Earth here now. GM1, M2 over R squared again. G is 6.67 times 10 to the minus 11. From the data table up here, the mass of the sun is 1.99 times 10 to the 30. And the mass of the Earth is still the same. 5.97 times 10 to the 24. Divided by the distance from the Earth to the sun, 1.50 times 10 to the 11. What, 1,000 times more than the distance from the moon to the Earth? You know how far the Earth is away from the sun? Like that's a big distance, right? 150 billion kilometers, 150 billion meters, kilometers. It's so far that light that we see, which travels at 1 billion kilometers per hour. Okay, 1 billion kilometers per hour takes 8 minutes to go from the sun to the Earth. It takes 8 minutes to travel that 150 million kilometers. 8 minutes. That means if the sun was to suddenly disappear, we wouldn't have any clue for 8 minutes. Maybe the sun doesn't exist right now. Maybe it blew up 7 minutes ago. Good news. The bad news is the sun blew up 7 minutes ago. The good news is we still have a minute of light left before we even know that the sun blew up. Okay, we're looking back in time. When we see the sun, we're looking at the sun as it existed 8 minutes ago. That's how far the Earth is away from the sun. If it takes 8 minutes for light to travel that distance, it's a big distance. Okay, let's calculate this number. 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30 times 5.97. This is the mass of the Earth times 10 to the 24. Press equals. Let's divide that by, in brackets, 1.5 times 10 to the 11. End bracket, square it, and we get, what, 3.5218 times 10 to the 22 newtons. An even bigger force. Why? Well, because the Earth is heavier than the moon. If the Earth is going to stay in orbit around the sun, you got to have an even bigger force, about 100 times bigger than the force that keeps the moon in orbit around the Earth. So we said F net is equal to the sum of the forces. It's the force of the moon on the Earth plus the force of the sun on the Earth. The force of the moon on the Earth, we drew that diagram, is to the left, so we're going to make that a negative value. Negative 1.9848 times 10 to the 20, plus the force of the sun on the Earth, which in our diagram is to the right, so we're going to make it positive. 3.5218 times 10 to the 22. Add these two numbers up, and that gives us the net force on the Earth due to the moon and the sun. So 3.52 subtract 1.9848 times 10 to the 20 gives us 3.50 times 10 to the 22. There we go. Positive value means the force caused by the sun is quite a bit bigger than the force caused by the moon. Got it? These are big forces, right? Big forces. Big enough forces to keep the moon in orbit around the Earth, big enough forces to keep the Earth in orbit around the sun, and big enough forces. What does the moon's force of gravity do to us every day? Big enough forces to cause tides, right? The Earth's water shifts because of gravity caused by the moon. That's a big force. Water's heavy. Okay, it takes a big force to cause that water to shift as it does. All right. I would like you, please, to take a look at page 209, and you can work on these for the last few minutes of class, but also for homework. Page 209. Try questions 1 and 2. Number 1, you should have no issue with because it's almost exactly the question we just did. But number 2, look at what happens in number 2. We get the moon up here, the sun over to the right here. Try number 2. Okay, I want to see what you can do with that. Okay, that's going to be a little bit of a challenge question, but if you use what we've just learned, combined with what we've already learned this year, I think you can do number 2 as well. So page 209, number 1 and 2, in addition to page 206 if you haven't finished those questions already.